When a modern database holds billions of records, locating a single entry by checking every row sequentially causes the system to drag. To keep applications responsive, we need a way to bypass the search process entirely. Hashing provides this bypass. It is a technique that uses the data itself to calculate its exact storage location in memory, allowing for near-instant retrieval. We store this data in a hash table. As this diagram shows, the table maps large inputs, like these 12-digit student IDs, into a small, fixed-size array. Each ID, such as 1234 or 5678, is assigned to a specific index row. The assignment is handled by a hash function. Using a common method like modulo arithmetic, the function takes a key, like 123, and divides it by the table size. The remainder, which is 3, illuminates index 3 on the table, marking exactly where that record lives. Because this mathematical mapping is deterministic, the system can find any key without scanning other records. This creates a search complexity of O of 1, the fastest possible speed in computer science. However, since table sizes are limited, eventually 2 different keys will produce the exact same remainder. This is the central challenge of hashing. Look at what happens when we use a table with 10 slots. If we apply our modulo function to the keys 25 and 35, both return a remainder of 5. When they both attempt to occupy index 5, they clash. This is a collision. We can resolve this using linear probing. Since index 5 is already taken by the number 25, the number 35 simply checks the next available slot. It shifts down 1 space and locks into index 6. If we zoom out, the downside of this method becomes clear. This creates primary clustering, where groups of filled slots form a bottleneck. Future searches must step through these entire clusters to find an empty space, slowing the system down. To prevent these bottlenecks, we can use quadratic probing. Instead of checking every single slot in order, the system uses an exponentially growing step size to spread the data across the table. From our starting point at index 5, the first jump is 1 squared, just 1 space away. If that's full, the next jump is 2 squared, or 4 spaces. The third jump is 9 spaces. These wider gaps help the data bypass existing clusters. While probing keeps all data within the original array, it can lead to secondary clustering, where keys still follow the same jump patterns. For more flexibility, we can change the table structure itself. This alternative is called separate chaining. Rather than hunting for a new spot elsewhere in the array, we allow each index to hold multiple values. As we see here, index 5 now acts as the head of a linked list. Keys 25, 35, and 45 all map to the same spot, but they are chained together by pointers. No data is moved, and no keys are overwritten. Implementing this in a language like C++ typically begins with a fixed-size integer array to serve as the foundation of the table. Here is the implementation for linear probing. The logic inside the while loop checks if a slot is occupied. If it is, the code increments the index and uses the modulo operator to wrap around to the beginning of the table if it reaches the end. Choosing between these techniques is an engineering trade-off. Probing is memory efficient because it uses a single array, while chaining is often faster in high collision scenarios because it never runs out of room. A developer must balance these factors: the simplicity of linear probing, the distribution of quadratic probing, or the flexibility of separate chaining. These mechanics are particularly important for data security, especially in the way systems protect user passwords. Instead of storing a plain text password, a database stores the hash value. Because this process is irreversible, an attacker who breaches the server only finds these complex alphanumeric strings, not the original passwords. Remember that the hash function is the mathematical tool used to calculate the location, while the hash table is the structure that actually holds the data. By combining efficient hash functions with the right collision handling, we can build architectures that are both secure and capable of processing billions of requests at top speed.